Good day, everyone. Welcome to Unit 2. We are delved into the fascinating world of vibration analysis for systems with 2 degrees of freedom. In our previous sessions, we explored general equation for 2 degree of freedom system. Now, we are taking it up a notch to understand how multiple interacting components affect the vibrational behavior of a system. Look at this diagram. We have two masses labeled M1 and M2 connected by a spring K. Notice that each mass can move independently, represented by the respective displacements x1, x2. This independence is what we define as 2 degree of freedom system. Our goal in this unit is to learn how to determine natural frequencies of such systems. Understanding these frequencies is crucial in engineering design to prevent resonance and to ensure stability. So, let's embark on this journey and unlock the secrets of 2 degree of freedom systems. Let's we solve the problem 1, which introduces us to a special type of system known as semi-definite systems. Take a look at this diagram. We have two masses M1, M2 connected by a spring. Notice that a masses can move along a horizontal surface indicated by the displacement x1, x2. The key characteristics of semi-definite system is that one of its natural frequencies is equal to zero. This might seem counterintuitive at first, but it has significant implication for how the system behaves. In this specific example, the zero natural frequency arises because there is no fixed support or external constraint preventing the entire system from undergoing rigid body motion. Imagine pushing both the masses together. They would move as a single unit without any internal spring deformation. Let's we explore this concept in more detail as we work through the problem. Understanding this kind of semi-definite systems is crucial in many engineering applications, particularly when dealing with unconstrained or lightly constrained structures. Let's see how we can able to determine natural frequency for this kind of fascinating systems. Let me determine natural frequency for this semi-definite system. We know that the displacement we are taking into consideration of mass m1 as x1 of t and mass m2 as x2 of t. When there is a slight disturbance in these masses, then there will be acceleration acting on these two masses. Then what will happen? So there will be accelerating force which is then equal to mass into acceleration. So let me form the equation of motion for this 2 degree of freedom systems. First thing, there is a accelerating force. So accelerating force equal to mass into acceleration. And then there is a stiffness force which is acting opposite and equal such that stiffness into displacement. Let we take one by one. For the mass m1, we are having the accelerating force, that is mass into acceleration. We can denote it as mx1 double dot, which is equal to and opposite the stiffness force. Stiffness means we have to multiply the stiffness into displacement. Here K is going to be having the two displacement. That means this spring force is going to be depends upon both x1 as well as x2. That means actually we are going to have only a difference in the displacement. That means x1 minus x2. So this difference will be acting on the mass m1. The similar fashion, this is mass M1. For the mass M2, we can write the accelerating forces as M2 x double dot, that is equivalent opposite to K. Once again, the same spring is acting between the mass M2 and M1. So the actual difference of these two displacements we have to consider as the displacement of the mass M2. So from this we can able to form equation of motion for this 2 degree of freedom system, that is m1 x1 double dot plus k x1 minus x2 equal to 0. Similarly, for the mass m2 x2 double dot plus k x2 minus x1 equal to 0. Let's see how to solve this simultaneous equation in the next slide. As derived from the previous slide, the equation of motions for this semi-definite systems are m1 x1 double dot plus k x1 minus x2 equal to 0, and second equation is m2 x2 double dot plus k x2 minus x1 equal to 0. Now we have to find natural frequency for this semi-definite system. In that case, I have to assume the solution such a way that the x1 will be a1 of sine omega t plus phi, where omega is the frequency at this the motion is going to be take place for a mass m1. Similarly, for x2 equal to, we can take it as a2 sine omega t plus phi. Here, A is nothing but amplitude, which is going to be continuously changing from 0 to 360 degrees. Since it is going to be the sine wave, so the vibration will be happening like this. So in that case, when I have to substitute both these terms in the equation 1 and 2, then what I have to do, I have to see what is going to be x1 dot, that is velocity. So if I differentiate x1 with respect to time t, then I will get a1 is constant, no need to differentiate it. So here I have to differentiate sine omega t because it is going to be t, differentiate with respect to t we are doing. So sine will become cos omega t plus phi. This omega will come outside and also minus term will come. Then x1 double dot, that is velocity is once again differentiated with respect to time. So we'll get acceleration. So minus a1 still remains. Omega already is there. Now cos omega t plus phi, if I differentiate, it will become a sine omega t plus phi plus another omega will come. Now this omega will be multiplied with the already existing one. So x1 double dot equal to minus a1 omega square sine omega t plus phi. Similarly, x2 double dot equal to minus a2 omega square sine omega t plus phi. We have to see that x1 equal to a1 sine omega t plus phi. Same thing, here we can apply this a1 sine omega t plus phi is going to be x1. So then what will happen? x1 double dot equal to minus a1 of x1, that is omega square will come into picture. Since it is going to be the same, then x2 double dot equal to minus a2 omega square. You can write in terms of a1, otherwise x1 also. If it is in terms of x1, we can write in terms of x1. Okay, that is, it means that If it is pi is going to be very small, x1 equal to a1 mathematically. Similarly, x2 equal to a2. In that case, this term a2 sin omega t pi is became as going to be the a2 itself. That is going to be the a2. So we can write it as like that. Okay. So this term. Okay, simply it will be the same form, plus omega square will be coming to picture. Otherwise, in simpler terms, if you want to write, it is very easy. Let me avoid the confusions. We will put the same term. Okay, then what will happen? So x1 double dot equal to minus omega square x1. It is very easiest thing you can able to remember. So a1 sin omega t pi is nothing but the x1. So you can directly write it x2 double dot equal to minus omega square x2. So this will be equation number 3 and 4. The next slide we will substitute x1, x2 in equation 1 and 2. Then we can proceed to solve it. From the previous slide, we came to this step, that is acceleration is equal to omega square terms of x1. Similarly, the acceleration of the mass m2 is x2 double dot, which is equal to minus omega square x2. Now, what we are going to do, we are going to substitute this one in equation 1 and 2. So if I am substituting it, what will happen? So it is m1, this x1 double dot I am going to substitute. Then in that case, it will become as minus omega square x1 plus k x1 minus x2 equal to 0. Similarly, here this will become as m2 omega square x2 plus k x2 minus x1 equal to 0. Now, what we are going to do means this is going to be rearranged in terms of x1 and x2. So if it is rearranged, then what will happen? So I am taking common terms x1. So it is k minus m1 omega square x1. Then it is k x2 equal to 0. Similarly, here it is minus k x1, then plus k minus m2 omega square x2 equal to 0. So in the next slide, we will solve this. In the previous slide, we substituted acceleration in the equation 1 and 2. So now we are going to write the equation 3 and 4 in determinant. So when I am writing in determinant form, it is k minus m1 omega square, then minus k, which is multiplied with x1, x2, that is equal to 0. Similarly, the next term, here it is minus k, then k minus m2 omega square, which is also equal to 0. Now we have to do the determinant. So just what I have to do, I am going to multiply this and this one. So what will be happen is k minus m1 omega square, k minus m2 omega square, minus of minus k will become plus k square, which is then equal to 0. Why? Because means here the displacement term x1 and x2 will not equal to 0, means then the determinant will become as 0. Now let me expand this in the next slide. So In the previous slide, we derived the equation from the determinant. So what it has been is nothing but k minus m1 omega square into k minus m2 omega square minus of minus k will become as k square equal to 0. Now I expand this. So it is k square minus k m2 omega square minus m1 omega square k minus of minus plus m1 m2 omega to the power of 4 minus k square equal to 0. Hence this k square will get cancelled. Now I write it in the space here. So what will happen here? This term I am going to write it first. Since it is omega power 4. So m1 m2 omega power 4. Then I am going to commonly take omega square outside. So what will happen? It is going to be omega square is going to be taken outside. So now it is going to be written as minus k m1 plus m2 into omega square. So which is then equal to 0. So you can see that I am commonly taking minus k outside, omega square outside. So m1 plus m2 omega square. So this equation is now rewritten like this. So in the next slide, from this, let me explore and complete what is the omega square is. That is natural frequency. So it has been found from the previous slide, that is from the determinant we can able to find out this equation m1 into m2 omega to the power of 4 minus k m1 plus m2 omega square equal to 0. Now I have to take omega square commonly outside. It is omega square commonly outside. Then what will happen? m1 m2 omega square minus k m1 m2. Already omega square is outside. It is equal to 0. So what will happen? It is easiest from this. Omega square is going to be equal to 0. That is omega 1 equal to 0. Then from this equation, m1 m2 omega square equal to minus k m1 plus m2. From this, omega equal to root of k m1 plus m2 divided by m1 into m2. This is the natural frequency of this semi-definite system. We can see that one of the natural frequency is 0 for the semi-definite system. So what will happen? System will not oscillate to and fro. It is just it will move. When it is pushed, it will move. There is no relative motion between mass m1 and m2. So in a semi-definite system, there is no motion between masses m1 and m2. It it is moving as a rigid body. So we have to keep in mind that in the semi-definite system, there is no motion between two bodies. It is moving as a rigid body. From this, we conclude the semi-definite system. In the next uh, discussion, we will move on to the next type of